Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 22. In this lecture, we'll discuss fictitious forces. This topic is covered in Chapter 6 of our textbook by Surway and Jewett. The concept of fictitious forces is somewhat abstract and difficult to understand. So as a warm-up, we'll first do a couple of practice problems. Suppose a pendulum that normally hangs straight down is seen to tilt at an angle theta. The mass is not swinging, the tilt angle theta is constant. What can you conclude about the forces acting on the mass? So we have a pendulum here, basically a mass that is attached to a rope or a string with the other end attached to the ceiling. Now, a pendulum normally just swings back and forth a few times and then eventually settles down at its equilibrium position, hanging straight down. That's not the situation here. As we observe this pendulum, we notice that it's tilted at an angle theta and it's staying there, so it's not swinging back and forth. This tilt angle theta is constant. Given just this bit of information, what can you conclude about the forces that must be acting on this pendulum? Well, presumably this is on planet Earth, so there must be weight acting on this pendulum. If we knew the mass of the pendulum, we could calculate the force of gravity or weight that's acting on it. Remember, weight is just mg. In addition to weight, there must also be a tension force acting on the pendulum. After all, the pendulum bob, the mass that is connected to a rope or a string or a cable. In all those cases, you must have a tension force. Whenever a rope is attached to an object, there is some tension acting on that object via the rope or the string. Now, these two forces are somewhat obvious, but obviously these two forces alone cannot account for the behavior of this pendulum. Weight wants to pull the pendulum bob straight down. Tension wants to lift it up and move it to the right. So if the pendulum is tilted at some angle theta, there must be a third force. In fact, there must be a force pulling the pendulum to the left, like so. At this point, it's not obvious what this third force is. We'll just refer to it as a mystery force right now. But even without knowing what this force is, just given the information at our disposal, we're forced to assume that it must be present because tension and weight by itself would not be able to tilt the pendulum to the left. If the pendulum is tilted to the left, there must be some force pulling it or pushing it in that direction. We can analyze this situation in a little more detail. In fact, we can even calculate the magnitude of this force F in terms of other quantities like the tilt angle and the mass of the pendulum. If we zoomed in on tension a little bit, we would see a situation like this. Notice that the tension force is tilted at an angle. So weight is, let's say, in the negative y direction, and the mystery force is relatively simple. It seems to be acting straight to the left. We could call that the negative x direction. But tension is along the rope, and we know that the rope forms an angle of theta relative to this vertical line here. If this angle here is theta, then this angle here must be theta. The magnitude of the force is T, and the tension force has an x component, which we'll call Tx, and a y component, which we'll call Ty. If you know the magnitude and the angle, then you can easily calculate Tx and Ty using a little bit of trigonometry. As you can see, you have a right triangle here, so you can use sines and cosines to express Tx and Ty in terms of the magnitude of the tension force and theta. A little more precisely, if we analyze the forces in the y direction, this is what we find. The sum of all forces in the y direction is equal to t cosine theta. Note that t cosine theta is basically the y component of t. So if we're looking at this angle here, theta, then Ty is adjacent to that angle, so Ty will end up being t cosine theta, and as you can see, Tx is opposite this angle, so Tx ends up being equal to t sine theta. So for now, I'm interested in analyzing the y forces. So I have t cosine theta minus mg is equal to 0. Mg, of course, is weight. The whole thing is equal to 0 because we're told this pendulum is not swinging, right? The tilt angle is constant. So presumably it's not accelerating. And of course, Newton's second law of motion tells us that the net force is equal to mass times acceleration. In this case, the acceleration is 0. This equation is quite useful because it allows us to figure out tension. So figuring out weight was easy, but to figure out tension, we needed this equation. And now we can calculate tension. If we have the mass of the pendulum and the tilt angle, then we can easily figure out the tension that would be present in the rope. Now, this equation doesn't tell us anything about the mystery force. In order to figure out the mystery force, we must analyze this problem in the x direction. So once again, we use Newton's second law of motion. The sum of forces in x must equal to mass times acceleration in the x direction. The sum of the forces in x is t sine theta minus the mystery force F. It's minus because the mystery force is pointing to the left. And all of that is equal to mass times acceleration in the x direction, which is presumably 0. So now we can solve this equation. We would have to take our previous expression for tension. So we can take this quantity here and substitute it for tension in here, in which case we'll get mg over cosine theta times sine theta. You might remember that sine theta over cosine theta can be written as tangent theta. So we can solve for f by a substitution and a little bit of mathematical or algebraic manipulation. We find that the mystery force F is equal to mg times tangent of theta. So this is quite a useful analysis because with very little information, basically the tilt angle and the mass of this object, we can figure out the tension in the rope. And although we don't quite know the nature of this mystery force, we can actually calculate its magnitude. We can figure out that a force of this magnitude must be there if the pendulum is tilted at an angle theta. To help us understand fictitious forces, let's do a second practice problem. Suppose a pendulum that normally hangs straight down is seen to tilt at an angle theta inside an accelerating truck. What can you conclude about the forces acting on the mass? Notice that this problem is quite similar to the practice problem we just finished doing. Once again, we have a pendulum. The pendulum bob is attached to a rope. The other end of the rope is attached to the ceiling, and the pendulum is seen to be tilted at a constant angle theta. The only difference between this problem and the previous one is some additional information. We are now told that this box that was enclosing the pendulum is actually the backside of a truck, and the whole thing is moving. The truck, in fact, is accelerating, and so the pendulum and everything else in the truck must also be accelerating. Given this additional piece of information, what can we now say about the forces acting on the pendulum? Well, presumably this is still on planet Earth, so W is still present. mg, gravity, is pulling the pendulum down as before. Gravity really doesn't care if the pendulum is accelerating or not. There is a rope attached to the pendulum bob, so there must again be some tension. But notice this time I don't necessarily need the mystery force. I can now explain the tilting of the pendulum by the fact that the truck is accelerating to the right. What's happening is that as the truck accelerates to the right, the top of the rope, which is tied or attached to the truck, is also going to accelerate forward. And that rope is basically going to pull the pendulum behind it. And so the tilt angle is really due to the acceleration of the truck, not due to a mystery force. We can actually make this precise. We can say that in this case, the pendulum and of course everything else in the truck must have an acceleration to the right. We'll just call that acceleration A. As before, we'll analyze the forces in the y direction. we do have tension. We can figure out the angles exactly like we did in the previous problem. And we find that in the y direction, we have t cosine theta minus mg, which is equal to mass times acceleration in the y direction. Presumably this truck is accelerating on a flat horizontal road, and so we can say that acceleration in the y direction is 0. So this is exactly the same equation we had before, and just like before, we can find the tension, and we find that the tension is, again, a function of mass and the tilt angle. So nothing new here so far, but in the x direction, things become a little bit different. Notice that I no longer need to invoke the mystery force to explain the behavior of the pendulum. I can now attribute the tilting to the acceleration of the truck. So I can simply say that the only force acting in the x direction is t sine theta, namely the x component of tension. And that must be equal to mass times acceleration in the x direction. Here we're calling that a, so I'm just going to write it as ma. There's no need to write or include a mystery force. And this last equation allows us to figure out the acceleration of the truck. So as before, we can take our expression for tension, this expression here, and we can substitute it in for t. And then once again, sine theta over cosine theta gives me tangent of theta. And with a little bit of manipulation, you find that the acceleration is equal to g tangent theta. So in some sense, we have basically designed a very primitive accelerometer. If you were inside this truck, you could measure the tilt angle, and based on the tilt angle, you could calculate the acceleration of the truck. Notice a similarity between this problem and the previous one. The physical setup was quite similar. However, before we were not told whether the pendulum and the room in which it's situated are accelerating, but here we have this additional bit of information that the whole thing is in fact accelerating to the right. So what do we learn from the two practice problems that we just completed? The essential moral of the story is that the behavior of objects, like a pendulum, can be attributed to either forces or acceleration, depending on the frame of reference, depending on how we look at the problem. In the first problem that we did, we were essentially looking at the pendulum from the point of view of a person inside the truck. It wasn't at all obvious that the truck was moving. We could not see the outside world. The only bit of information we had access to was the fact that the pendulum is tilted. We knew nothing about its acceleration. In fact, if you are the person inside the back of the truck, you would see that the pendulum has 0 acceleration relative to you inside the truck. And from that perspective, in that frame of reference, you would conclude that there must be 3 forces acting on the pendulum. So the mass itself has 0 acceleration, and to explain the tilting, you have to essentially invent a new force and say that this third force must be present in order to explain the tilting. However, if you step out of the truck and stand by the side of the road, let's say, and look at this truck, and imagine this truck has sort of like a glass wall so that you could look inside it, you would not need to invoke a force to explain the behavior of the pendulum. You would just notice that the truck is accelerating relative to you, and therefore everything inside the truck, like the driver and the pendulum and any other cargo that might be in the back of the truck, must all be accelerating to the right. And now we can use the acceleration to explain the same exact behavior, the tilting of the angle. In fact, we can even calculate A in terms of theta, or vice versa. If we know A, we can calculate the tilting angle. So there is a duality here in how we explain the behavior of objects. It seems that sometimes we can explain the behavior of the pendulum or other objects by invoking forces, while at other times we can explain the same behavior by invoking acceleration. And at this point you should be wondering, well, which is the correct explanation? So as we just stated, the behavior of a system, at least from a mathematical point of view, can be explained either in terms of forces or acceleration. As it turns out, it's the second explanation in terms of acceleration that is correct. In an accelerated frame of reference, it may appear as if a force is acting on an object, but in fact there is no such force. Such a force is called a fictitious force. So a fictitious force is a force that appears to be there, but it's not really there. It appears to be there specifically because you are measuring forces in an accelerated frame of reference. You've probably experienced fictitious forces yourself if you've ever been in a bus or a train that suddenly stopped or suddenly began moving. Imagine yourself, for example, standing up in a bus, minding your own business, maybe just looking at your cell phone, when you suddenly get thrown forward, when you suddenly lurch forward. At that point, hopefully you're smart enough to realize that the bus must have suddenly stopped. You realize, hopefully, that throwing forward was not a real force. Hopefully you won't turn around and pick a fight with the guy behind you because you think he pushed you. No one pushed you. No one exerted a force on you. The feeling or the sensation of there being a force was simply the result of you being in an accelerated frame of reference. The bus was moving with some constant speed. Then suddenly the brakes were applied, so the bus slowed down, right? That means acceleration. And that acceleration created the sensation of a force, but the force was in fact a fictitious force. There are other examples of fictitious forces. You may have experienced the centrifugal effect or the Coriolis effect yourself. The centrifugal effect is sometimes referred to as the centrifugal force, especially in older textbooks, but you should avoid that terminology. The centrifugal force is not really a force. At best, it's a fictitious force. So in more modern terminology, we refer to it as the centrifugal effect because it's not really a fundamental force. It's just the result of things being in an accelerated frame of reference. More specifically, both of these effects are the result of things being observed in rotating frames of reference. To appreciate the centrifugal effect a little bit better, imagine yourself driving your car around a sharp turn in the road. As you take this turn to the right, you're effectively executing circular motion. Remember that to execute circular motion, you need to have a radial acceleration of minus v squared over r. So as you're driving your car around this turn, you are sitting in an accelerated frame of reference. You might feel, as you take the turn, that something is pushing you to the left. If you have some fuzzy dice hanging from your rear view mirror, you might notice that the fuzzy dice tilt to the left, very much like the pendulum we were just discussing. So you might think there is a mystery force, a centrifugal force, pushing you and the dice to the left. In reality, there is no such force. In reality, the fuzzy dice and you are simply trying to move along a perfectly straight line. It's the car that is moving to the right. So the acceleration of the car to the right gives you the sensation of a force pushing you to the left. Okay, so that force is sometimes referred to as the centrifugal force, but try to avoid that terminology. The Coriolis effect is a little more complicated to understand. The Coriolis effect is responsible for the rotation of hurricanes on planet Earth. You may know that hurricanes on planet Earth always rotate in a very specific way. Here is a picture of Hurricane Katrina from 2005, and as you can see, this hurricane is essentially rotating in the counterclockwise direction. As it turns out, all hurricanes in the northern hemisphere rotate counterclockwise, whereas hurricanes in the southern hemisphere rotate in the clockwise direction. Again, it might appear as if there's some mysterious force controlling the rotation of hurricanes in the north and the south, but in fact this is happening because these hurricanes are forming in an accelerated frame of reference. The frame of reference in that case is planet Earth. Planet Earth is rotating So these hurricanes are effectively executing circular motion around the Earth's rotation axis, and therefore the hurricanes are in an accelerated frame of reference. So the situation we've described so far is probably a little confusing. Essentially, we began by saying that mathematically we can explain behavior in terms of forces and acceleration. And then we proceeded to say that, well, you have to be careful because in an accelerated frame of reference, forces appear to be there that are not really there. These are referred to as fictitious forces. And now the question is, well, how do we distinguish between real forces and fictitious forces? When I observe the behavior of an object, how do I know if there is some kind of a ghost force or a fictitious force acting on it, or whether it's a real force like tension or friction or the normal force? Basically, what we want to know is what is the true cause of an object's behavior. To answer that question, we must first define the notion of an inertial frame of reference. An inertial frame of reference is a coordinate system with zero acceleration. So an inertial frame of reference is basically a person that is making observations in a frame that is not accelerating, in a frame that is moving with a constant velocity. It doesn't have to be zero velocity, but whatever the velocity is, it must be constant so that the acceleration of that observer or the acceleration of that frame of reference should be zero. A free particle, a particle that is not experiencing any forces, a particle that is not interacting with any other particles, would move with constant velocity in an inertial frame of reference. So the reason the idea of an inertial frame of reference is important is because henceforth we will agree that all forces must be measured in inertial frames of reference. So henceforth, if you want to study the behavior of a pendulum and you're wondering why is it tilting to the left, what are the forces acting on it, the first question you need to ask yourself is, am I making this observation in an inertial frame of reference? Am I guaranteed that things are not accelerating? Are you looking at the problem from the perspective of a non-accelerating frame of reference? If so, then you can proceed to measure forces, and whatever forces you measure or calculate will be real forces. On the other hand, if you happen to be in an accelerated frame of reference, so in a non-inertial frame of reference, then you cannot rely on your measurements of forces. It is quite possible that there will be fictitious forces involved. So to be able to distinguish between real forces and fictitious forces, we must agree to make measurements or perform experiments in an inertial frame of reference. In other words, before we do any calculations or measurements or experiments, we must first establish that our frame of reference, our point of view, our reference system, or our coordinate system is not accelerating, then proceed to measure or calculate forces. Now, as it happens, most physics experiments are done on planet Earth. Occasionally, astronauts conduct experiments in outer space, for example, inside the International Space Station, but the vast majority of all engineering measurements and physics experiments are done on planet Earth. So a natural question to ask is Earth an inertial frame of reference? Well, let's find out. Earth can be modeled as a sphere with a radius of 6.371 times 10 to the 6 meters and a mass of 5.972 times 10 to the 24. The Earth rotates about its axis once every 24 hours. Calculate the radial acceleration of a point on Earth's equator due to its rotation. So here we're not talking about the rotation of Earth around the sun. We're talking about the daily rotation of planet Earth, the rotation around its own axis. This rotation, of course, happens every 24 hours. And what that means is that any point on planet Earth is essentially executing circular motion. The center of that circle would be somewhere on the axis of the planet. Now, if objects are executing circular motion, then you should be thinking that there is some acceleration. So as you sit in your chair, you're executing circular motion. You complete one giant circle every 24 hours, okay? And this is true of you and your house and your school and your physics laboratory. So everything on Earth is basically going around circles, and therefore there must be some acceleration. We can calculate that acceleration. To calculate the acceleration, we need to first know the speed with which the planet is rotating. We're going to, for the most part, concentrate on a point on the Earth's equator. A point on the Earth's equator basically travels around the circumference of the Earth. The radius of that circle is basically the radius of planet Earth. So I can calculate the distance that is traveled using the circumference formula, 2 pi r. Plugging in the radius, I find the distance that is traveled once around the equator is 4.003 times 10 to the 7th meters. And the time, of course, is 24 hours, although you want to convert that to SI units. So spend a few seconds doing that conversion. Converting 24 hours to seconds, we find that that is equal to 8.640 times 10 to the 4th seconds. And then putting all this into our calculator, we find that a point on the Earth's surface at the equator is moving at an astonishingly fast speed, 463 meters per second approximately. So if an object is traveling around a circle with this speed, what must be its acceleration? Well, we know that the radial acceleration is equal to minus v squared over r. We have v, we have r. Plug all that into your calculator, and you will find that it's minus 0.033693 meters per second squared. So in fact, any point on planet Earth does experience some acceleration, and therefore no point on planet Earth is really an inertial frame of reference. In other words, we should be very suspicious of any measurement or experiment that we do on planet Earth. We should always be wary of the fact that the Earth is rotating, and therefore some of the forces that we measure may be fictitious forces. The Coriolis effect that I was discussing earlier is an example. Now, in case you're wondering, well, does this mean that none of the experiments I've ever done in a physics laboratory are valid? The answer is no, they are probably quite valid still, simply because this acceleration is very small, right? This acceleration is small, and therefore Earth is approximately an inertial frame. Technically, it's not, but the acceleration is quite small, and therefore we can trust most of our measurements. However, for ultra-precise measurements, you need to consider the fact that there is some small amount of radial acceleration. And that's the end of this lecture. Thank you for your attention.